Hello, Chem 1A. This is Chapter 7, Lecture Video 2, and we're going to be discussing two laws of gases. So there's quite a few of them, and we'll be discussing most of them in this chapter. In this video, we're going to discuss Boyle's law and Charles' law, and these really talk about how different properties of gases relate to one another. Boyle's law specifically is all about how volume and pressure are related when both the amount of gas and the temperature of the gas are held constant. So pressure and volume are inversely proportional. As we increase the volume, the pressure goes down, and as the pressure goes up, the volume goes down. Basically, as one goes up, the other goes down, and this is true as long as both temperature and the amount of gas stay the same. Now, this can be related in an equation, and I'll provide this equation on the next exam, so you don't need to memorize it. And that is P1, our pressure under our first condition, times V1, and the volume here doesn't matter what unit you're in as long as you're consistent across the equation, as well as pressure. Pressure could be in torr, millimeters mercury, atmospheres, any pressure unit's fine, as long as both P1 and P2 are in that unit. And this equals P2, our new condition, and our new for volume and pressure. So let's do an example problem. We have a sample of nitrogen gas, and it has a pressure of 67.5 millimeters mercury in a 500 milliliter flask. What is the pressure in atmospheres of this gas when it is transferred to a 125 milliliter flask at the same temperature? So we have our equation, P1V1 is equal to P2V2. Now, it doesn't matter what units we plug in here. However, we do know that P1 is going to be our initial condition of pressure, so 67.5 millimeters mercury. V1 is our initial volume, which we're told is 500 milliliters. P2 is what we're being asked to solve for, and V2 is 125 milliliters. Now, we can throw all these values into the equation right now as it stands if you want. That'll calculate, when we calculate P2, that'll be in millimeters mercury though, and we're specifically asked for it in atmospheres. It doesn't matter when we convert to atmospheres. We can convert this to ATMs first and then do the problem, and then our P2 will be given in atmospheres, or we can solve for it first in millimeters mercury and then solve for atmospheres. And that's the second option is what I'm going to do. So we have 67.5 millimeters mercury times 500 is equal to P2 times 125 milliliters. And if we rearrange this to solve for P2, we get P2 is equal to 67.5 millimeters mercury times 500 milliliters over 125 milliliters. And as you can see, the milliliters here cancel, and we're left with our answer in millimeters of mercury. This gives us 270, with a dot there for sig fig purposes, millimeters of mercury. Now, I don't want that in that unit, so I'm going to go, hey, divide this by 760. Millimeters of mercury is in 1 ATM, and this gives me my final answer, which is 0.355 ATMs is my answer. All right, so let's talk about a new law here. This is Charles' law, and Charles' law relates volume and temperature to each other when both pressure and amount of gas are held constant. Now, as it turns out, that the volume of a gas is directly proportional to the absolute temperature of the gas. Now, this absolute means something very specific. It means we have to be in units of Kelvin for our temperature. So, in other words, as the temperature in Kelvin increases, the volume of the gas also increases. So we have an equation here that's slightly different from the previous one, but similar. It has V1 over T1 is equal to V2 over T2. And so we're comparing an initial condition to a final condition in this type of equation. Let's do a sample problem with this. So in this case, we have a 5 ml sample of CO2 is enclosed in a gas-tight syringe at 22 degrees Celsius. If the syringe is immersed in an ice bath until the temperature is 0 degrees Celsius, what is the new volume, assuming that the pressure is held constant, right? So I have 5.0 milliliters. I'm going to call that V1. I'm being asked for V2 in the problem, and we know T1 is 22 degrees Celsius. V2, again, what we're trying to solve for, and T2 is 0 degrees Celsius. Now, before I do anything, we have our equation V1 over T1 is equal to V2 over T2, but I cannot use it yet because these temperatures are in Celsius. I need to first convert to Kelvin. And so what I get here is that T1 is equal to 295.15 Kelvin, and T2 is equal to 273.15. At this point now I can solve for the volume, right? So I have 5.0 milliliters over 295.15 Kelvin is equal to V2, what I'm trying to solve for, over 273.15 Kelvin. And we can rearrange and solve for V2. I'm going to do this over here. So V2 is going to be equal to 5.0 milliliters times 273.15 Kelvin all over 295.15 Kelvin. And as you can see, the Kelvin units, they're canceling. We're left with our volume in milliliters, and you should get about 4.6 milliliters of gas. This has 2 sig figs, so our answer should have 2 sig figs as our answer here. All right, if you have any questions, as always, please let me know, and I'll see you in office hours, hopefully.